Everybody get a binder? Everybody? Well, there are 20, there are like 18 people in here, so I suspect we're missing one. Good morning.
Right.
Here. So, welcome back. You had a good summer. A little short, in my opinion. This is Science of White Words, all right? So, I don't have a book yet, though I doubt that will ever actually happen. So what I've tried to do initially is to put things together in the binder for you. You'll see there's 9 homework assignments. You already know I don't grade homework assignments, right? That's not going to change. But I will try to publish or post an answer set to the homework assignments on or about the due date. Okay? And so what I'm trying to do is get you to read the literature, you know, basically synthesize the lectures or figure out how to use that information so that you have a pretty good understanding of what's going on. There's a syllabus in here. The schedule is what I hope will happen. And that sounds like a great idea, of course. It never really works the way that I plan it. But if you look at the schedule, there's a couple things that are going on in here, and there's MS&T is coming up. That's going to be in Portland, and I'm out that whole week. And I don't know when that falls. It's somewhere around here. 26th of September. I think I'm leaving on Wednesday, something like that, which means we'll probably have classes that my other classes won't be. I know that's a little bit early, but I have other things to do in Portland. And then I get back the end of the following week, so you have a whole week off. So of course, I'll have an exam during that time because I don't have to be here. Fair enough. Okay. Exams are essentially, there's 2 exams and a final, and they follow the sections, and they're listed in here. My intention at the moment, because I've missed some days, is to make the second exam a take-home. We can discuss that, of course. And it will only be on these sections, Section A, Section B, but the final exam is everything. Good? Okay. The exams pretty much make up your grade. That's listed on the bottom of this sheet here. All right. And his research paper and project, I haven't really scheduled that, put that in. So I'm going to debate that and we'll see what happens. It's a bigger class than I normally have, which is fine. There's a whole bunch of references here. There's no book. There hasn't been a book published on white words in a long time. These books here, you can probably find copies of them in used bookstores. Science of White Words, there were 2 editions. There were 3 conferences, but the 3rd conference proceedings never got published. That one wasn't actually my fault. Ceramic Engineering and Science Proceedings used to be the 2nd issue every year. They would come out, and then what happened in the United States is that the white word industry left the country, more or less. Greed took over, right? Somebody figured out, by not doing the math very carefully, that they could make money by having China made in China. And that was true for a while, as the Chinese government subsidized utility energy costs, right? And then when that went away, it turns out that it's no cheaper to make China someplace else than it is to make China here. But by that time, the factories were closed for the most part. There are still a few manufacturers in the U.S. A lot of the data I'll show you was generated with Buffalo, China, for example. We used to work with them very closely. They were, as you might imagine, in Buffalo. They were huge. They made 28 million pieces of China a year. They consumed something like, maybe it was 21 million, and they consumed 28 million pounds of raw materials to do that. It was a huge operation. Raw materials came in typically at that time in rail cars. This isn't like 1950, this is like 1985, or 1985, excuse me, that it might be before most of you were born. 2000 into about 2005 or so. By rail or truck, rail cars hold 45 tons of material, 90,000 pounds. Okay, so they would do something like, I don't know, 14, 15 rail cars a week, something like that, maybe a little bit more. So it was a huge operation. Syracuse, China, guess where they were. And then you had Sterling, China, was in Wellsville, Ohio. Hull, China, in East Liverpool. East Liverpool was a small, you know where East Liverpool is? East Liverpool, Ohio. It's at that tip of West Virginia in Ohio. You know how West Virginia has that little finger that sticks up. They were there. At one time, there were 200 potteries in that area. Most of them mom and pop shops, right? Small places that would make pottery. And then they would fire like every 2 weeks. Okay, something like that. Homer Laughlin is still there making China. They make Fiesta ware. This is Fiesta ware, not this. This is Fiesta ware. This is Fiesta ware though from the 40s probably. Okay, what a great orange. How do you get that orange? This is awesome, by the way. You can't do it after the 40s. You know why? No, you can't. You can't get this orange after the 40s. Because you couldn't put uranium in glazes anymore. Because you can't get uranium, right? There's a problem getting uranium today. If I plan ahead, which is very likely, we'll bring in the Geiger counter because this is awesome. All right? This is what it looks like today outside of the dirt. It's really not a good comparison between the two, right? But this is how they do it today. Homer Laughlin, though, this is Fiesta ware. If you look at their back stamp, I'll pass this around. It says lead free. And so the issue is, lead used to be really common in glazes. Buffalo, China still used lead in glazes up until when they closed. I'm not a real fan of magic. In fact, I hate it. Yeah, the probability of finding me at a magic show is pretty close to zero. But lead is the closest thing to magic that you're going to find in ceramics. What it does for glaze durability, quality, longevity is just remarkable. And LaCourse worked on this for a while, deciphering why glazes are so durable under such conditions is tricky. It doesn't correlate perfectly with hardness, it doesn't correlate with density, it doesn't correlate with a bunch of things. But lead is sort of an outlier in the way it behaves. So, Homer Laughlin, early Fiesta ware like this, not only do you have the uranium in here, it's a lead glaze, and that's part of why it's such a brilliant color and brilliant finish. I'll pass this around also. A friend of mine had these, and they wrapped it, in, her father wrapped it in lead and let it sit in the attic for a long time. Anyway, that leaded glaze was done properly, and then family went to Mexico. This is a story, never verified it. Family went to Mexico and found a knockoff of Fiesta ware, which is really common. You go to antique shops, you know, they'll always tell you that it's really Fiesta ware, but you flip it over, it doesn't have that back stamp on it, it's not Fiesta ware. So they went to Mexico, they found something that looked like Fiesta ware, and they bought it. It was a green pitcher, basically, and it was an improperly fired lead glaze. So they put orange, not because of that, but they put orange juice in it, they had tumblers. And then the orange juice, right, reached the lead, and the family got lead poisoning, and they tracked it back to the Fiesta, the fake Fiesta ware, and Homer Laughlin almost went out of business, stopped making Fiesta ware for like 30 years. Okay, and then when they came back, it says lead-free. They developed lead-free glazes, get around the problem. Anyway, entertaining. There's some other books in here that are really great if you can find them. Orton's Fine Ceramics, Technology and Applications, and Elements of Ceramics are really good. They're hard to find. London's Studies on Traxial Ore Bodies is Traxial Porcelains or White Ore Bodies is impossible to find. Introduction to Ceramics has a good thing on porcelains, and where Kingery got that was from London, so you have access to that. I would say ceramic engineering and science proceedings were published up until whitewares industry went away, and at that point, the whitewares division of the American Ceramic Society more or less became dormant, is the word they used. And then a few years ago, we transformed the division into a manufacturing division, so there's still, there are still porcelain manufacturers in the country. Lennox China still makes porcelain dinnerware in North Carolina. And then there's a few others. I think Picard China is still being made, and a couple others, but they're mostly gone. What's not gone are tile and electrical insulators. And so down here in the front, you see the electrical insulator. Okay, that actually failed on cooling, and pretty rare. It gives you a great cross section of what that looks like. It's actually upside down, by the way, but it's more stable that way than if I stand it the other way. Here's another example, and you can see the cross section, right? Inside of here, this is called a sand band, okay? And then they put either neat Portland cement, for example. You know what neat Portland cement means? Not like it's cool. No aggregate, no sand, just Portland cement. And they put that in there, and then they have a metal pin, okay? And then that metal pin is locked in place mechanically. There's not any appreciable chemical bonding in the system, and then an end cap. So this is actually a suspension insulator. There'd be a bunch of these stacked together. I don't know who cut it in half. They did a great job. And they even rounded the corner so you can't cut yourself without a lot of work. And but this is how they make insulators. If we have time, we'll visit Victor Insulator up in Victor, New York. They still make insulators, as well as Lap Insulator. And there's a couple others, Newell Porcelain in Newell, West Virginia, which, by the way, is next door to Homer Laughlin in West Virginia. Lock Insulator used to be in Baltimore. They have now closed. ICI was up somewhere between here and Victor. I should know it, I can't remember. They've been closed for a long time. Electrical insulators are still being manufactured in the United States and in Mexico, partly because they're really heavy and expensive to ship. The quality of electrical insulators is generally really good, okay? And they have to follow ANSI standards in order to sell to the insulator, to the utility companies. Okay? Porcelain is still preferred. The competitor now is plastic. What's the problem with plastic? Outside of we don't like it and we don't use it. Is it deteriorates in sunlight. And they've been working on that problem, but they still haven't solved it. Plus, the really big post insulators like this down here, you know, where you're 50,000 volts or 70,000 volts, you can't do that with plastic yet. Okay. Linemen really like the plastic insulators because they weigh a lot less. Also, you can toss them in the back of the truck and they don't break, but porcelain is still preferred even in the industry. Let's see. I've broken the class up into 3 sections. It took me a long time to figure out how to do this. And raw materials and processing first after an introduction, talk about what's going on in porcelain. And then we'll get into forming, which is actually the smallest section, and then firing and glazing and properties and things like that. I'm going to post a lot of things on Canvas for you to read. Okay, I printed out 3 things in the back of your binder for you to read. One is an outdated review article that I wrote with Udi and Senapate, who's a postdoc of mine, in 90, I don't know what it was, 98 maybe. And he was brilliant. But I say it's outdated because since this time, we have learned a lot. Okay, so we started a research center here in Alfred called the Whitewater Research Center. Okay, and at that time, so this is 98, the center was formed around 94, and we basically had buy-in from the manufacturers and raw material suppliers. And at the peak of the Whitewater Research Center, there were 21 companies involved. And what they were funding was what's called pre-competitive research. In other words, if you want to make a red glaze, that's your problem. If you want to understand how glazes work, then that would be something we would work on. Okay? And in that course of time, we published roughly 40 master's or PhD level theses in this subject. And so this class actually started out with artists and engineers in the same class. And artists would propose a problem engineers would work on as a project at the end of the semester. But that became difficult as we kept knocking off these understanding and concepts of why things happen. Okay, so when it started off, it was like, well, we see this problem with cracking. Okay, cracking could be due to this or this or this, and then you can kind of work within those boundaries. And then we came down to this is how it's caused, or this is what caused it, like crazing glazes or what have you. When it evolved from ideas on why things happen to specifics of why they happen, understand? Like generation of graduate or undergraduate level research that identified the problems, right, and the causes. Then we had a problem because either you teach the class, where you teach the analytical tools, right, which would ideally bore you, or you teach the class with the assumption that the analytical tools, this is how we know, in which case you wouldn't be able to necessarily keep the artists up. Don't misunderstand, I mean, they're very smart and they understand the materials very, very well. When you get into the analytical part of it, it makes it difficult. So I teach ceramic science for artists separately in the summertime, and I teach problem solving for artists as a seminar in the spring, but we separated the two at that time. That was about maybe 10 years into doing this. So there's a bunch of stuff in this article that's wrong, which is kind of cool, actually. You get a homework assignment for that, too. We'll find something wrong in the article. It's not very difficult. And then, you gotta ignore the picture of me, which is horrible. Microstructure of porcelain. This guy, Sten London, this is 1964. 1957, he wrote his thesis. He was from Sweden. He was not a ceramic engineer. And the benefit of that was that ceramic engineers had been told that it was too difficult to understand the mineralogy, microstructure evolution, etc. in porcelains. And since he wasn't a ceramic engineer, he didn't know that. So he went ahead and demonstrated how to do it. He used phase diagrams to explain what was going on in porcelain. Really brilliant work. And then he published this. The top says Microstructure of Ceramic Materials, Miscellaneous Publication 257 from the National Bureau of Standards in 1964 as part of the proceedings. And then the funny thing is if you look at this, then you look at Kingree's Introduction to Ceramics, the same figures show up by and large, particularly microstructures. So London figured out what was going on in porcelains. Really well done. And then the last article in the group that you have, I want you to read all of these, of course. This is really brilliant work done. This is just the cover, sorry. Influences of variable silica and aluminum on porcelain glazes with constant RO, and should be 2 in there probably, R2O plus RO, by a professor at U of I called Stoll. And he published 2 articles. I'll give you the second one also. 1912, this was published. Brilliant, really brilliant. And the reason it's fascinating. So the reason that this is so interesting and the reason they did it was because of an architectural change that occurred in the early 1900s. Do you know what that is? What big architectural change started occurring in residential houses in the late 1800s, early 1900s? See, you just take it for granted now like it's not a big deal. Bathrooms came inside the house. How cool is that, right? What's the problem? Oh, wall tiles would craze over time, right? Humidity in the bathroom, right? And then the wall tiles would, moisture expansion, they would expand, and then the glazes would craze, right? And so Stoll wanted to understand why glaze was crazed. And he wanted to map glazes to figure out how they craze. Well, that, in and of itself, is awesome. And the reason that it's awesome is because Griffith, right? Remember who Griffith is? Who's Griffith? Yeah, father of fraction mechanics, right? What did Griffith say? Oh, Griffith, excuse me. Griffith, 1920. Oh, wait a minute. Stoll's doing this in 1912, doesn't understand brittle failure, doesn't even come along as a concept until Griffith in 1920, right? How cool is that? You know, so what we have here is, this is Stoll's diagram that he developed. All the open circles that you see are glazes that he tested, okay? And what he was looking for was this boundary here that comes down and goes back up. This, all this shaded region is where glazes craze. Okay? So what he did was he mapped it all out. He didn't understand at the time brittle failure, right? So we now know, and we've known for a long time, that glazes craze because the thermal expansion coefficient of the glaze is greater than that of the body. So when you cool the system, the glaze contracts more, places it in tension, and it cracks. Now the cool thing about that is if you measure the spacing of those cracks, which we started doing about maybe 10 years ago, you can predict the thermal expansion coefficient difference between the glaze and the body, which is also cool. But he was trying to find glazes that didn't craze. And what he found was something even more interesting. He found boundaries for behavior. These are matte glazes here. These are bright or gloss glazes. And these, he says, are devitrified, which is actually incorrect. Devitrified then indicates that they were vitreous, and then they crystallized on cooling. Okay? And that's not true. Those, and that's, we're not faulting them. But what we find now is those glazes are under fire. Okay, so that means that it wasn't hot enough for the raw materials to melt to form the glass in the firing process. And so the consequence is you get matte glazes down in the lower right, but they are sensitive to firing conditions, in other words, temperature in particular. So if you take that glaze and you put it in the top of the kiln where it's hot, or in the bottom of the kiln where it's cold, the texture of that glaze will be different. And it will change with kiln location, or location of the kiln, right? But the crazing thing is fascinating because the crazing thing is linked to the thermal expansion of the body. And we find that that boundary is actually pretty close for the stuff that we test as well. So I'd like you to read Stoll's article. There's another one that he wrote also with, I assume, a grad student named Howitt, and they mapped the melting points of those materials. Porcelain industry has evolved dramatically. We started essentially here. I have shards from China. I was in China in May, actually. Some of these I've had for a long time. I'm missing the one from the Song Dynasty, but this is Yuan Dynasty. This is somewhere around 1,000 years old. Song Dynasty one is probably the oldest piece of my collection other than a rock, right? They're pretty old. But as a man-made object or as a manufactured object, this is actually press molded. So 800 to 1,000 years ago, they would take a mold and they would carve the pattern in that mold, and then they would press the clay, and so they were duplicating those patterns, which is quite remarkable. Pass this around. The reason I have it, right, is because things that weren't perfect had to be broken, right? So if you're making china for the emperor, you can't take home the pieces that don't work, that have defects in them, because then you get executed. It's kind of a big deal, okay? So nobody could have imperial china except for the emperor, so anything that's left over gets broken. So you go to these kiln sites, and there are broken shards everywhere. Now there's a problem with that, right? What's the problem? Any defect gets broken. So you don't know if it was properly fired, but there was a blemish, or properly fired and say the setter failed and the pieces fell over and stuck to the side of the sagger. You don't know whether it's that, or whether it was grossly underfired, grossly overfired. Okay. My last trip I found this, which is awesome. Doesn't seem like it's awesome. Is that awesome? This is awesome. This is a setter. And so at this time frame, the setters were essentially saggers, but they carved into the wall the place where the piece would sit. You know, and it's like, this looks like it could have been made, you know, like yesterday. I didn't find a very big piece. Well, the big pieces I could fit in my pockets. There's a problem there. So, China, porcelain was invented in China, right? In the typically Song Dynasty, so you're 900 to 900 AD, roughly, to something like 1200 AD in that time frame. That's not quite right. And I have a sort of Eurocentric view that it was an accident. And the reason it was an accident, that I think it was an accident, was you had, at the time, feldspar was not a common raw material. So let's take a step back. We think about what's going on here. These are called triaxial whitewares because there are three components. Okay, we have a simple diagram looks like this. We have molite here, which we're going to talk a lot about that. Actually, molite here, excuse me. This is metakaolin, which is essentially clay. And then you have feldspar here. And this is quartz, or silica, okay? Down here is lucite. The reason I showed it to you that way is that we have a line across here, a dashed line, and our porcelain compositions typically sit in this area. And they are three components: feldspar, clay, and quartz. So we have roughly 50% clay, 25% feldspar, and 25% quartz. Okay? Somebody asked you the composition of a porcelain body. That's pretty much it. We can vary around that. You know, you can jack up the clay level. You can drop the, you can increase the flux level. So the feldspar is the flux. Okay? And that's what provides the material to form glass. Right? The clay is in there, provides plasticity and does some other interesting things. And the quartz has been termed in the literature inert filler, which is absolutely wrong. It's not inert at all. All right. So we're going to play with phase diagrams this semester. You will be experts in phase diagrams, probably by mid-semester, but definitely by the end of the semester. Okay. This all comes out of the potassium aluminosilicate phase diagram. That's what we have here. Lower left-hand corner is potassium. Top is silica, technically cristobalite, okay? And the bottom right is aluminum. And so I say technically cristobalite because this is an equilibrium diagram, right? You had phase diagrams before, right? So that means that these are equilibrium conditions. Fair enough? Okay? Which we don't usually see in reality, but it's a change in phase diagram. The red triangle you see here is actually what I replotted here. Okay, so here is lucite, here is potassium feldspar, here's molite, and you notice that metakaolin isn't on the diagram. And the reason that metakaolin isn't on the diagram is because it actually is the decomposition product of clay. So this actually has a composition, which is this. Okay, and if it was clay, it would have on the end 2H2O, but we don't have water on the diagram, so we can't represent it that way. So essentially, if I heat up my clay and lose the water, then I can plot in the phase diagram. Okay. Now, Kingery redrew the diagram. This diagram has been around for a long time. There's a lot of interesting things about this diagram. You notice this line that goes from silica all the way down here. What you see along that line, this is something to pay attention to, is that the ratio of any of these two components, potassium and alumina, is the same for every point along that line. That's a property of a ternary diagram, right? So you have 1 potassium, 1 alumina, 1 silica, 1 potassium, 1 alumina, 2 silica, 1 potassium, 1 alumina, 4 silica, 1 to 1 to 6 for feldspar, so they all fall in that line. That's pretty slick, right? And so, and here's 1 potassium, 1 alumina. Those are all stable compounds within this phase diagram. If I want to know where clay sits, I have this 1 alumina, 2 silica. Here's 1 alumina, 2 silica. I can draw a line from potassium through that point to here, and that would be where metakaolin would sit. Don't worry, we're going to play with this some more. Kingery redrew the diagram like that. Okay? And he shows us then, so he did a little bit of work, Kingery. He redrew London's diagram to make it more accessible, and then he plotted on here compositions. So hard porcelain semi-vitreous whiteware sits here, vitreous tile and sanitary ware sit here, and electrical insulators sit here. These are the temperatures at which those materials would be fired. Cone 12, cone 14, cone 16, roughly What are cones? Anybody work with cones? Anybody done pottery in here?
Temperature readings.
Yeah, they're a temperature indication device, right? Turns out that I had planned ahead in your thing here, you have a chart of cones. It's in the first few pages. You'll also see in the first few pages that you have Stahl's diagram, and then you have this melting behavior diagram that Stahl did with Howitt 2 years later, or 2 years later. And then periodic table. This is sort of a different periodic table. This periodic table has is for glass formation. It indicates how these oxides behave in glass forming, which is really a big deal in porcelains and glazes. The yellow with the blue square in the middle, it's designed so you can make a Xerox copy of it. This is before we had color copies. And those are fluxes, so they help to melt, right? And then you have the glass formers, which are the red with the red square with the black dot in the middle, like silica and phosphorus, which we don't care so much about, antimony. And then you have the intermediates, like alumina, for example, and then there's some that are sort of in between that, like glass forming intermediate, etc. So this helps you see glass formation. And then when we flip to here, there's Pauline's rules for silicate, and then here's your parametric cone chart. Okay, so you get an idea. This is a big deal. So actually, I just got a paper to review that looks at deformation of cones. So they're not dead. They're really useful. They were developed in 1895 by a guy named Sager. Okay, which is all this stuff is happening a long time ago. Sager was a German scientist. 1895, he started looking at porcelains, published a lot, developed a lot of ideas around porcelains. And one of the things that he did that's enduring is parametric cones. Orton happily borrowed his idea of cones, so now we have Orton cones. Okay, but Sager invented them. And the first cone that he invented was, of course, cone 4. Why? Because he did the cones from a standpoint of chemistry, which is a really interesting idea at the time. Okay, and if you look across here at cone 4, it's got 2 stars by it because that's the first cone that was made. All right, and then his temperature, and then the temperature that we now know is correct. So based on 1895, I mean, you can give him some slack if he's off by 20 degrees, right? But the issue was that he made this cone up, and what you look at is the fluxes here, 0.3 to 0.7, so potassium and calcium, right? It equals 1. So what we have is called a Sager formula, or what we now call a UMF, a unity molecular formula, okay? And when we have a unity molecular formula, we compare the chemistry of the system to normalized flux level. Okay? So in every system we look at for glass, then, the fluxes are 1 mole. Does that make sense? Everything is normalized to flux. So the fluxes are 1 mole, then what we have is a very easy way to look at our chemistry. So when we go to Stahl here, you see down here in the bottom, it says cone 11, and at the time, wall tile were cone 11, 0.3 to 0.7 potassium to calcium, right? So this equals 1. So it means every point on this plot has a flux basis of 1 mole, and then these are all the molar ratios. It says molecules, right? Molar ratios. 0.4 alumina for 1 mole of flux, 0.4 moles of alumina, and then I can come over here and say, oh, and then 3.6 moles of silica. So that's how that works. I don't understand why we don't do this globally. Artists always do this. It's a great way to look at chemistry of glasses. Really great way to look at chemistry of glasses. Why? Let's say I increase the silica level. right? Let's say I make a glass, I decide I want more silica. So I add silica into the glass, okay? Here, on this diagram, if I add silica into the glass, I simply move horizontally, right? If I'm doing it on a mole percentage basis, now all the percentages change, right? So if I add silica to the glass, my flux level will go down, my alumina level will go down. Then my ability to sort of interpret what's happening in that glass is going to be difficult. If I do it on a weight basis, I'm just wasting everyone's time. Fair enough? Because one, we should do everything on a molar basis, then we're comparing apples to apples, right? And two, this UMF approach that Sager invented in 1895 really helps me understand how these things develop, okay? And how glazes evolve and how bodies occur. Let's go back to the cone thing for a minute. We're going to talk about cones, but only a little bit more as the semester progresses. Cone 4 was first because cone 4 had 4 moles of silica. It's actually remarkably logical, right? And then cone 5, oh look, it had 5 moles of silica, and then cone 6. It even did pretty well until you got to 10, then wheels came off the bus, but I didn't care so much about that at the moment. But this is where he started. So then somebody said, well, I need lower temperature. So then he went back down, and he went to cone 1, okay? But he did it by adding iron. Now, he didn't treat iron as a flux at the time. Iron's clearly behaving as a flux. It's reducing the melting point. I should ask you that. What's the definition of a flux? Say again?
Added that serves to reduce the melting point
Of
the glass.
silica. Good. No, I mean, it's exactly right. Something that reduces the melting point of silicon. Okay? That's a flux. And so, if you think of calcium and potassium as a flux, right? But iron is added in, and it increases or decreases the melting point, it must also be added as a flux. What's the problem? The problem is the way that Sager looked at it is as R2O, RO, R2O3, RO2, right? And so these are your sodium and potassium, for example, lithium. Okay, this is say magnesium, calcium, barium, strontium. Okay, R2O, first alumina, right? Now I have a problem. Okay, my problem is I can also include iron in here, right? I can include boron in here, which really confuses the world. Okay, and that's a problem. We'll address that. Iron, though, shows up 2 ways: Fe2O3, FeO, in reduction, right? And FeO behaves like calcium, and Fe2O3 behaves like alumina. So what really should happen is that he should treat Fe2O3 as FeO. It should go up here and act as a flux. Okay, fine. And then RO2, you've got silica, that's the big one. Then you have titania, you have zirconia, okay, etc. So because he grouped them that way, then he looked at iron that way, and it doesn't help us understand what's going on. So he gets down to cone 1, that sounds great. And then somebody came in and said, you know, we'd really like to measure temperature below cone 1. So then O1, O2, O3 were developed later. They go down to, as far as I know, O22. Okay, and O20, you know, so those are really low melting point systems. Cones are essentially glazes, right? They're not bodies, they're glazes. So they actually behave very much like the glaze. When you heat them up, they deform and they come down, and then you can actually measure temperature really well. At the time this was being done, thermocouples were basically non-existent, right? So you put cones in the furnace, in the kiln, and you can look in a peephole and you can see the cone, and when the cone comes down, the cone that you want, shut the furnace down. Okay? We still fire that way. Wood firing, for example, really common to do that way. Now we have really sophisticated devices, optical pyrometers, thermocouples, etc. And that's fine, but cones are still reliable. The other thing that's great about it is you have a big furnace, right? You can stick cones all over the furnace, and then you can map the temperature distribution of the furnace, which is really difficult to do any other way. Industrial furnaces like tunnel kilns that run continuously, so cold to cold, right? And the temperature goes up, essentially distance equates to temperature. They'll put cones in. With every third or fourth car will have a cone pack on it. So then you can verify that the temperature in the kiln is what you think it is. Thermocouples are great. They're great for control. Okay. The cones are nice. They are essentially passive heat measurement devices. They work very, very well. The tunnel kiln thing brings up one other thing. This is obviously a tile. I'm not going to pass this around. This is a porcelain tile. This is essentially, right, 2 by 2, right? It's been polished. And this material, though, right, fast fire. Cold to cold for this material in 50 minutes, 5-0, which is staggering. So electrical insulators, heating cycle times are from basically about 36 hours to 4 days, 96 hours. They fire this in less than an hour. Ceramic tile, not porcelain, 38 minutes. There is nothing sane about that. That's ridiculous, right? But the thing that's really ridiculous about this is, I think, let's say it's 600 millimeters. It's 2 feet by 2 feet, roughly. Not 600. Yeah, 600 millimeters, something like that. They're now making tiles that are 2 meters by 3 meters. You got to think about that for a second, right? 2 meters by 3 meters, right? We're working with a company that's developing that material for countertops, and they go in and they machine out the holes for the sink or whatever, right? And they'll make them from roughly 1.5 centimeters to 3 centimeters thick, and they're firing that in 50 minutes. Now, it's a roller hearth kiln, right? Single layer kiln. Material comes in one side is green, right? Compacted, it's dry press product. This is color all the way through. You can see that from the edge. They're now doing things where they have color just on the surface and then no color below that. I mean, whatever the color of the body is. Why do you do that? It's cost, right? Color is the most expensive thing you put in the body. So they'll make the top layer colored and the bottom will be uncolored. 2 meters by 3 meters. Think about that. Based on the speed that it's going through the kiln, the front end of that tile is hot and sintering before the back end starts to sink. That's crazy. Yes.
I think you can fly. Do you think like with that level of just like difference?
There's a lot of things I don't understand, and that's probably one of them, right? Although I have a great example of that, but I'm going to talk about that in a second. But everything that you know about sintering, have you all had sintering? We have it this semester. Who has it this semester? You all have it. Great. How do you get cracking in sintering? Do you get cracking in sintering? Did you talk about that? Or was it all theory and no application? Basically theory. All right, so we have this illusion. It's a great illusion. Propels us in our industry, right? And it makes us invaluable to people making ceramics. And that is that cracking occurs on firing. Fair enough? Think about this. What is wrong with that picture? If I can take a tile, then so the argument is, oh, I heated too fast on one end versus the other. Nonsense. It makes no sense at all. If I can take a tile that is, even if I run it through the kiln with the 3 meters is perpendicular to my direction of travel, see what I mean? So you only have 2 meters. You're still talking about that thing shrinking on one end before it shrinks on the other and holds together. I think we have to rethink everything we know about sintering based just on that. Right? Anything that we see that occurs on cracking in the kiln has to then be due to the forming process, not to the firing process. Fair enough? Our defects are invented in forming. They just show up in the firing process. Even the way that we compact tile and do the dry pressing is phenomenal because it has to be a uniform green density or it warps. Right? Now, there's a great, this was a really great, this was really fun. There's a company in Mexico, I don't know the name of it. They show up in my office one day I don't even know how they got on my calendar. Show up in the office one day and we have a problem. And they're making tile that's about this big or maybe a meter square. And so they have the tile, right, like this. And they only have color on the top half, right, like that. And then it comes out of the kiln, it's flat, okay? And then they polish it, good? So this is a polished surface. We like the polished surfaces, they're beautiful, they look like they're glazed. Sometimes they glaze these, but the glazes aren't as durable as the porcelain, right? So the porcelain durability is similar to that of granite, better than marble, similar to granite. Love it as a wear surface, right? When you put a glaze on it, it's not that durable. The glazes aren't. So they fire it, they polish it flat, and then they go back and they measure like later in the day, maybe the next day, and now it's not flat anymore. It's perfectly flat when it comes out of polishing. And then a little while later, it's not flat anymore, it warps. This is such a great problem. Why? You want to go take 5 minutes and talk about it? I'll take 5 minutes and talk about it. Okay, what do you know? This is important, what do you know? Wait, what do you know? I told you, you didn't hear me. Where's it made? Mexico. Good, let's start there. Okay, now before you get like all Eurocentric on me or whatever, it's not about Mexico. All right, what else do you know? What? Well, you know that's hot in Mexico, that's good.
Only one part of it has the pigment.
One part has the pigment, good, right? So if you think about the cross section, you have this, right? And this is a pretty good line here. I mean, my approximation isn't so bad. This is colored, this is not. Good? Oh, by the way, sometimes it warps up, right? Sometimes it warps down. Such a great problem.
You know what they use to make pigment?
Probably something with zircon in it. Don't care. How's the pigment affect things?
Different colors.
Yeah, makes the color different. You're good. You're really good. Pigments change the color. Good. You use something. All right, so it's probably true too. So, right, color, pigment changes the color. What else does it do?
Density?
What's that?
Density?
Yeah, it might increase the density. How does that affect warping?
CTE.
Good. Tell me about CTE. Who said CTE?
Coefficient of thermal expansion.
Good. Tell me how coefficient of thermal expansion is a function of pigment level. You are on the right track. Why do they polish it though, and then later it warps?
Would the polishing like heat up the top?
Ah. So how do you polish? How do you polish? Anybody polish from here? I hope. How do you polish?
Right.
How do you polish?
With some kind of grit sandpaper that you then, etch away material and.
I get that. That's the polishing. How do you polish? You go downstairs to polish.
Polish on these little wheels, but they polish on larger things.
So, do you polish dry? Does anybody polish dry? Really? You polish dry? Where did you work? Well, that explains it. You use water to cool the system, right? So actually, it's not heated, it's cooled. Polishing cools the piece. Got it? Right? Then what happens?
The heating and the now polish.
Nope.
You put it down somewhere
Yes, where do you put it?
in the sun in Mexico.
Well, you actually don't put it in the sun.
Well, in that case.
Okay, I'm entertained by that, but, all right, so, no, so you polish and you're water cooling the system, so it comes out perfectly flat after polishing because the tile is cold. And it sits in the warehouse, or it sits in the factory. Factories are not climate controlled, right? Temperature in the factory is significantly warmer than your polishing temperature, so the piece now warms back up. It warms back up, it warps. Why? Because you have a CTE mismatch between the color layer and the body. If the CTE mismatch, so it warms up, right? So if it warms up, that means that in this case, right, we'll say color on the top. CTE of the color layer is then greater than CTE of the body. How do I get that? Oh, because the CTE is greater for the color layer. So here's my color layer, right? So now when I warm the system back up, the color layer expands more than the bottom, causes it to warp down. Here the CTE of the color layer is less than the CTE of the body, right? So now when I warm the system back up, it curls the other way. How cool is that? Now, the interesting thing is, if they were in a northern climate, it could still happen, except they are in Mexico, right? So there's that temperature difference. In a northern climate, what would happen is different. It would be seasonal, right? In the summertime, it goes one way, in the winter, it might go a different way, right? In the summertime, the factory could be hot, but you're probably not going to see a difference between summer and winter, but you can see a difference between spring and fall and summer and winter, right? Because in the winter, you heat the building, in the summer, you don't. Building's roughly the same temperature, okay? But in the spring and fall, building could be cooler or warmer depending on what's going on. So you would see differences, seasonal differences associated with this. How do you solve the problem?
Temperature control?
What's that?
Temperature control?
No, I mean, you're stuck with that, right?
Bring them all the way through.
Well, you could do that, but then that costs you money. So what you have to do is you have to engineer the body to have different, to match the CTE between that which has color and that which does not, right? So, you know what's great about this, I do a lot of consulting, and when things work, I don't hear anything about it, I don't know what happens, right? It's only when they don't work that they come back and go, that didn't work at all. It's like, okay, I get that. All right, so, this porcelain tile thing is a big deal. And it's probably now the largest manufactured porcelain product anywhere. Smallest factory that you can build today to make truly smallest factory to mass produce tile is somewhere on the order of 1 million square meters a year. So they're not messing around. Let's go back to here. Hate this slide. The thing is that we have another problem in porcelains, by the way, and that is that nobody can decide what to call them. All right, and then I love the Spaniards. They really do. They've done huge things for improving our understanding of porcelain and tile in particular. They invented nanocrystalline or nanoparticle inks, so now you can print. Looks like wood. You'd be hard pressed if you didn't know it was porcelain to know it wasn't. Okay, they've built up all this technology. A lot of it just goes to China and gets duplicated, which is really part of it in the Spaniards. They dramatically improved their yields. They figured out how to use Spanish clays to make tile, immensely productive. But then they did something that really torques me. They make it porcelaneous stoneware. What the hell is that? You know, they just make up terms. And then you've got another one now. This is my favorite. This is last few years. Sintered stone. Okay. So, general terms are porcelain. Okay. And then you get stoneware, which is a different category. U.S. Customs defines them differently based on whiteness and water absorption. Okay. China is someplace in there, and it has sort of a designation. And Hotel China, for example, earthenware is typically underfired or not dense. So earthenware is low density, low strength material, right? It's what you get at Walmart or Kmart or whatever. Okay. By the way, we used to have a Kmart here. We don't anymore in Wellsville. I encourage you to go look. What's the woman's name? Martha Stewart. Okay. Go look at Martha Stewart dinner plates, and you will learn immediately that she has no understanding of crazy, by the way. It's awesome. I'm going to pass this around. This is broken for a reason. This is the stoneware body. It's red, okay? The glaze is green. If this was ancient ware, like ancient Korean celadons, for example, the glaze would have been applied clear, and then by interaction with the body became green. This is very likely applied as a green color already with iron oxide in the glaze. But I want you to look at the crazing, because this is a really great example of crazing. They call that a fisheye glaze, and we've not played around with it very much. But if I go back to, so China used to mean that it was bisque fired. So we have a two-fire process, very common still. Very, very common in art. You bisque fire the body, okay? And by bisque firing the body, you create a hard, strong body that you can then glaze. The downside is there's no shrinkage to speak of in bisquing, right? Why is that a problem? Because then defects that you generate that haven't shown up yet will show up in the final firing when you take it up to peak temperature, right? So that means that you bisque low and glaze high, right? And that argument was sort of a porcelain designation, but then to bisque high to fully densify the body and then glaze and fire lower was designated China. So it's a subtle difference. I'm not going to ask you that as a homework question or as a question on an exam because I don't care. Okay, but the China versus porcelain is sort of that designation of how the glaze temperature with relation to body temperature. Okay, earthenware, like I said, low strength bodies. Okay, if the glaze is in a lot of compression, they will chip. Porcelain, sanitary ware, right? We call that after dinnerware. You have electrical insulators, you have hard porcelain, which is hotel ware, none of you are tracking right now, and methylene cyanide is a substitute for feldspar. If I go here, there are these three zones, right? Electrical insulators at cone 14, sanitary ware and tile at cone 12, and hard porcelain at cone 16. This was true when this diagram was generated in 1976. It's no longer true. Here's the question, right? What dictates the differences in the temperature for those three bodies? What a great question. So I've got sanitary ware at cone 12, I've got electrical insulators at cone 14, and I have hard porcelain at cone 16. Ignore the semi-vitreous thing. Semi-vitreous means they didn't fire it hot enough. Okay, so we're not going to play with that. That's more your earthenware. What dictates the temperatures? So you have a couple things going on here. This is a paratectic 1140. This is a eutectic at 990. What's it mean to have a eutectic? My God, we're talking about phase diagrams on the very first day for the second time. What's it mean to have a eutectic?
Lowest point.
Lowest melting point. What's the difference between a paratectic and a eutectic? Okay, so intersection of the phase fields. So you have, this is the molite phase field, this is silica, this is a feldspar sliver of the feldspar phase field, this is the lucite phase field here. So I have feldspar here, I have molite down there, I have silica up there. This composition triangle or phase triangle, right? The intersection of the three phase fields lies within that triangle. It's a eutectic. Don't worry, we're going to talk about this again, okay? So it's a eutectic. That means that anything within this triangle of molite to feldspar to silica all start to melt at exactly the same point. And that point is the eutectic 990. That's where the first liquid is formed for any composition which lies within that triangle. Good with that? Okay, you will be? All right. So how come these three bodies have three different firing temperatures? They all start to form liquid at the same temperature. So, it's somewhat of a trick question. It's because the industry dictated the firing temperature based on the properties that they needed out of the material. And that sort of tells you something, right? What that tells you is that we have a broad range of firing temperatures possible with porcelains in the first place, which is one of the beauties of the material. If I'm on the low end of the firing cycle, I can get properties similar to if I'm on the high end of the firing cycle, right? So I have a firing range. Really well-designed bodies have a very broad firing range, okay? That means that in the furnace, in spite of the temperature variations from top to bottom, your products will come out with similar shrinkage, similar strength, similar appearance, right? We like that in a manufacturing environment. That makes the world work, okay? These temperatures, though, electrical insulators, your interest is high strength. So they fire at 14. Okay, it's not that 14 gives you high strength, it's that they're looking for optimum strength because they're going to take this insulator or the other piece and they're going to suspend them on poles, right? Or they're going to cantilever them out and hold out an electrical wire that could ice up in the wintertime, for example, or be subject to wind loads, substantial, right? You've driven down the street and seen the electrical wires moving around. That can't be easy on the insulator. So they have this strength, right? And that insulator might be on the pole for 60 years. There's an article that was published in the September issue of the American Ceramic Society Bulletin in 2017, and really pissed me off. And the guy argues that porcelain is not stable. Okay? I wrote a rebuttal. It shows up in January of 18. I'll give you both. Okay? And the problem is that he publishes that article, and I end up in litigation cases associated with electrical insulator failures. Now I have a problem. You can see how this would go, right? I'm on the stand as an expert witness, and the plaintiff's lawyer comes up and says, well, you know, blah, 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 do you publish? Of course I do. You know, do you publish in this journal? Yes, I do. Well, here's an article in this journal that says that porcelains are unstable. What do? I go, yes, I wrote a rebuttal to that in 2018. So, here's the problem, right? He argues that these things will fail with time, and they don't. So we started an experiment. About a year and a half ago, about 2 years ago, we made roughly 2,000 extruded rods, okay, at Victor Insulator. Quartz porcelain, aluminum porcelain, we'll talk about that later, glazed and unglazed. And Max Madugo, never could pronounce his last name, you know what I mean. He did the project and he measured, and we're doing this. 0.01, 0.03, 0.1, 0.3, 1.0, 3.0, 10, 30 years. Okay? My last paper will be when I'm 86. How cool is that? Right? Samples are currently stored on the roof. We have data up to here. And what we're doing is we're letting them age. Right? In here in Alfred, rare day, sunshine, okay? Snow, wind, rain, you know, cold. They're up there experiencing those changes in weather as an insulator would on the pole. Only differences are not under load, but that's okay. Right? And then we're measuring the strength of those rods, Weibull statistics, the whole deal. Okay? And we have now 5 data points. What do you think's happening? Nothing. What do you think will happen? Nothing. Good. But, you know, you can say, well, why are you doing it? That's the whole point, right? If nothing happens, then not only is this guy wrong, which I pointed out in my rebuttal, but in a very nice way, okay? It's that it's not going to change. This material is not intrinsically going to cause reduction in strength. So cone 14 for electrical insulators was for strength. Cone 12, what do you want there? You want it to be impervious. No one wants sanitary ware that absorbs water. The other thing you don't want, perfectly obvious, you don't need translucency. Fair enough? Right? So you don't care about translucency. You don't really care about strength, only care about water absorption. When you look at a toilet, right, they glaze where you can see it. Anybody worked at Kohler? Did they glaze the trap? Now they do. Why do they glaze the trap now? You know what I'm talking about? The trap? Do they glaze the trap now?
Wait, say it again.
You know what the trap is, right? So where you have,
Do they have the, yeah,
do they glaze the trap?
they do, but they use magnesium chloride now to strength.
Say again?
They use magnesium, I think, if
Oh,
I'm.
that's all wrong too. We don't have to talk about that. Okay, but they don't glaze typically they don't glaze the trap. They started glazing the trap about 10 years ago. Somebody started glazing the trap to improve the flow of water for low water consumption toilets, right? That the roughness here created turbulence and created a drag in the system, and they figured out they glaze the trap. Typically, they don't glaze the trap, right? So, I mean, the bowl is here, right? Right? And basically, you only see, if you look down here, it's glazed only as far as you can see it, right? Because, one, the glaze is not there to prevent water absorption. The glaze is there to make it easy to clean and to make it look nice, right? So that's cone 12. Cone 16, though, for hotelware was about translucency. So if you fire the piece hotter, it becomes more translucent. Okay? But those temperatures were not based on the phase diagram or on the melting behavior. They were based on the properties that they wanted out of the material at the end. Okay? We have a couple minutes left. So what we did several years ago is that we measured the chemistry of the glass phase for 100 different samples. And since that time, many more. And what we find is that the chemistry of the glass phase is remarkably uniform. And it falls in this line. Okay? And this line is roughly 1.2 moles of alumina per mole of flux. We're back to our UMF view of chemistry of glass. 1.2 moles of alumina per mole of flux. It doesn't fluctuate. It's 1.2 moles of alumina plus or minus 0.1, which is a really narrow margin, okay, per mole of flux. And then what happens is as we change temperature or change quartz particle size to a very limited extent, we can then, if I go up in temperature, I dissolve more silicon in the glass. But that ratio of alkali, in fact, alkali plus alkaline earth, if I have calcium or magnesium in the porcelain, which is relatively rare, to alumina stays fixed. And the reason it's fixed is because we argue that this is the glass formation boundary in the system. In other words, if I am to the left of this boundary, and recognize this is a small triangle of a larger diagram, if I'm to the left of that boundary, I have good glass formation behavior. And if I'm outside of that boundary, I get a glass ceramic, if you will, or I get a material that wants to crystallize on cooling. And where do I sit? My compositions sit in here, and I'm in the molite phase field, so that means I'm going to form molite on firing. There's no way around it because I sit in the molite phase field. But this composition boundary is a big deal. So we can then predict exactly how much molite will form in a porcelain body, because the amount of molite forms is the amount of alumina left over after the alumina is in the glass phase. Okay? So if I have more alumina than I need to saturate the glass, I form molite. And I can predict exactly how much molite I'm going to form in the system, which we'll talk about later. And, so you have a homework assignment, and this is what I would recommend that you do. There's a lot of stuff in here. There's basically, this is your first homework assignment. I want you to work in groups, okay? You recognize that you can turn it in if you wish, but it's going to be like a lot of my emails, you know, I'm not going to read it, all right? So, but I want you to do the homework assignment, and I will endeavor to publish an answer key. So why don't I grade homework? Because I don't do it in a timely manner, and then you submit the homework question, and then I mark it wrong. It doesn't help you. You know, well, what did he want? So this way you see what I want and how I want to do it. Otherwise, I got to spend a lot of time grading, but I won't do it until like the day before the exam, which won't help you at all either. So the other thing is that we got taking a very pragmatic approach to teaching. So here's what I propose. Between now and up through September 6th, you can ask anything in class about the homework. You can, if you want to meet with me, I'm perfectly fine with that. If you email me, you just delay the process. I do not have office hours. You already know that, right? But I have a great administrative assistant, okay? Email her, stop in, get on my calendar. I don't have office hours because I won't keep them. Something else gets in the way, that goes, right? I'm not going to be, I don't sit in my office from 9 to 10 every day waiting for someone to show up. It just not happen, okay? So go to Krishna, email her, she'll put you on my calendar. What's great about that is if she puts you on my calendar and something happens like delayed or you get overwritten, she will contact you and reschedule you automatically, right? Which is much better than working with me, okay? And then I'll meet with you. if you're working as a group on a homework assignment, try to come as a group. But you're better off to ask the question in here. If you don't want to do that, we will try on Canvas to set up a, what do they call it, a forum or whatever, where you can post questions. If you post a question to Canvas, you need to email me and tell me that you posted a question to Canvas, or I won't look at it. Right? I just don't watch Canvas at all. All right? But if you post a question to Canvas, you can do it anonymously, and then I can answer that question, or I can bring it in here, and we can talk about it in here. Fair enough? Okay. Any questions? Great. Enjoy your day. Enjoy your week. Welcome back.